Hi, welcome. I want to introduce to you my favorite Jurassic Park character, Mr. DNA. He would tell you that DNA is a blueprint to building any living thing. That includes your physical attributes. So, like whether you're short, tall, blonde, or brunette, all that comes from your DNA. And why is this important? It's important for forensic science because we can use that to create a composite for a suspect. And so today I'm going to talk to you about the innovation of DNA phenotyping and how we can relate it to the hair, eyes, and facial structure of a suspect. I'm going to start off with hair, but before I get into that, I wanted to discuss what DNA phenotyping is. DNA phenotyping is taking samples of DNA, which you can get from your blood, and you can test it for what physical attributes you have, which is the phenotype part. Phenotype means your physical attributes, and those come from your parents, so like generations before you pretty much give you all the traits that you have now. And so we can put these together and take blood samples from crime scenes, and we can test them for their physical attributes to determine what a suspect might look like. And so going on to hair, we can look at the DNA and look at the KITLG gene. We can look at it and determine whether someone has brown hair or blonde hair. And so I have a little sample of stranded DNA that I'm going to show you right here. As you can see, there's a ton of C's, A's, T's, and G's. So C represents cytosine, A represents adenine, T represents thymine, and G represents guanine. All those you can see within all the DNA strands. And so here we have C, A, C, T, A, A, G, and then we have at the bottom one C, G, C, T, A, A, G. You can see that there's a slight difference between the adenine and the guanine. We can see that the adenine goes to brown and the guanine goes to blonde. You can see that slight difference can determine whether or not someone's going to have a certain phenotype. And so all of this we can get from DNA, which is beneficial. While this is all great news, there are some setbacks, just because we never know if someone dyes their hair. Obviously, if I were to dye my hair blonde, you can't tell in my blood. But we also have age, which is also a factor. Age, sometimes when you're younger, you go from like blonde or like a lighter color to a darker color. But also as you get older, you go from the normal color to like a grayish color, gray or white. And so sometimes it's not always accurate in what color hair someone has unless we were to find like hair samples. But besides that, it's really good at determining someone's hair color. And not only can we look at someone's hair color, but we can look at someone's eye color. With eye colors, we have brown, blue, hazel, green, all those gorgeous colors. And so we can look at the OCA2 gene and the HERC2 gene to determine whether or not someone has a certain eye color. And so I have a little sample here, just kind of like before, except for without the letters. Here we have a HERC2 gene normal and an OCA2 gene normal, which make it a brown eye. Then, I don't know if you can tell, but there's a little red line right here for the HERC2 gene, kind of symbolizing that it's a little bit different than the first one. Then we have the OCA2 gene normal, just like the first one. And that leads to blue eyes. And then we have another one, which also shows the HERC2 gene being normal like the first one, and the OCA2 gene being different than the first two. But that also leads to blue eyes. So all these different genes can work together also to determine whether or not someone has a certain trait. And so this is all good, but there are some setbacks just like before. The more the intermediate colors, so the green and the hazel kind of colors. Gorgeous colors, but a little bit more difficult to tell. Just because blue is a recessive gene, and then the brown is the dominant gene. Dominant overpowers the recessive. So when you put those two together, that's how you kind of get the green and the hazel, but you could also get brown. So it just makes it the likelihood that it's accurate, it's just a little bit lower. But other than that, it does wonders for determining eye color. And not only can we look at eye color, but can we also look at the facial structures of humans. We have eyebrow distance, we have nose bridge, eye distance, face shape, all those wonderful things that we can see within genes. And so specifically, I'm going to look at the PAX3 gene, which looks at the eye nasion area. It looks at the inter-eye width distance. It looks at the nose tip right there. And it also looks at the bridge of the nose right there. So we can see all these little different pieces working together to determine whether or not someone has a certain characteristics. And those all just come from the PAX3 gene alone. And so what we can see is that we can look at a ton of different features from that one gene. While there are some setbacks, just like before, again, it's like kind of like facial morphology, which comes kind of environmental changes, like, oh, you had an accident, like you burned yourself, or like you hit your head, like all those little things, or you got like plastic surgery. All those like environmental or personal choices that you decided to take can also change, but obviously you as a scientist might not know that because it's not in their DNA. But otherwise it does wonders. And so today I told you about how we can look at someone's hair color, eye color, and look at their facial structure from their DNA. This is going to be a great innovation for forensic science, and I can't wait for you guys to maybe even take a second and dive into it a little bit on your own. And if you ever really care about your facial features, go complain to your parents. Tell them it's all your fault.